Hey there, Math 2403. Here we are in unit number 8. We'll be talking about linear regression today. This is a bit of a departure from what we've been doing. It's not full of confidence intervals and hypothesis tests, although they are in there. It's basically fitting a curve or a line to a scatter plot. So you've probably seen this before in other places. Today we'll discuss where it comes from. Let's get to it. Our goal for linear regression ultimately is we'll study the relationship between two or more variables and then build a model and ideally be able to make a prediction about one variable based on another. Quick example here, if I have the stress on an alloy, I'd like to predict the time to rupture. Before we build the model for such things, we'll first define something called correlation, which is just the strength of a relationship between two or more random variables. So we'll come up with a way to measure that with the correlation coefficient, actually. Here are some examples of two variable cases where I have a variable x on the x-axis and a variable y on the y-axis, and I can see that given a value of x, I can make a reasonable prediction about what y would be. This is a positive linear correlation because it's following a line, and it has a slope that's upward. Here's a perfect positive linear correlation where every value of y falls right on this line given a value of x. And then we have negative linear correlation, and then perfect negative linear correlation, just negative slopes. And then, oftentimes there's maybe no correlation between the variables, just a random scatter where given a value of x, you have pretty much no idea what y might be. And everything doesn't have to be lines. Certainly, we have this plot here where the two variables are highly correlated, but they don't necessarily follow a linear pattern. We could come up with a model for this as well, and it would be a pretty strong correlation, as given any value of x, I have a pretty good shot at picking what y would go with it. There isn't much variation there, as opposed to this one, which isn't nearly as good as, say, this one. So we want to come up with a way to measure the quality of the correlation. Certainly, this negative linear correlation is better than this one, and then there's many options in between. And there are options that are worse than this. Say, what is the difference between this one and this one? So we'll come up with a numerical measurement for that. It's called the Pearson linear correlation coefficient, relatively recently devised. He only died in 1936, so that's relatively new for mathematics. The coefficient is called R. It's an attempt to measure the strength of that linear relationship between paired values. This formula will only apply when you already detect that you have some sort of linear trend. The formula could be useless if your data, for instance, you shouldn't apply this formula to this parabolic looking data. This formula is devised for the linear case. We'll have the sample version R, and then the population value will be the Greek letter R, or rho, which unfortunately looks like a P. So what will be the assumptions to use such a formula? We need paired data, which is randomly chosen, and we need to have a bivariate normal distribution. That means that for each x, if you collect a bunch of y readings, that the y values would follow a normal distribution. And if you chose a y, the x values would follow a normal distribution, which is sometimes hard to verify, actually, because you don't usually have enough readings at each value of x or each value of y in order to verify that. So we have to sort of verify that assumption in an indirect way. How do we interpret this correlation coefficient? Well, if it's a number between, it's always a number between -1 and 1. Close to 0 means bad or not very well correlated, but close to 1 or -1 means that it's a strong correlation. So a value like 0.999 means you have a strong linear correlation with an upward slope, and a R of -0.999 means you have a negative strong linear correlation. It doesn't matter which variable you call x or which variable you call y, you still will get the same result for your correlation coefficient, which is a nice property of that. So we don't have to have a strict rule about what is the independent variable and what is the dependent variable. The correlation coefficient doesn't care. It's just measuring the relationship between the two variables. There are generalizations of this to more than two variables as well. Obviously, we'll use software to do this calculation. You saw the formula for it is, not very friendly. You have sums of products and individual sums that we then take the product of, sum of squares for each variable, it's not it's tedious to do that by hand, especially with any large data set. So we'll pretty much rely on our calculator or software to do this. So that's how we will interpret this value. We have to pause here to make sure that we don't make commit one of the deadly sins of statistics and say that correlation and causation are necessarily the same thing. Just because two variables are correlated doesn't mean that one is necessarily influencing the other. You can find interesting, strong correlations between variables that are completely unrelated. You can find that as the number of pirates in the world has decreased, the number of cancer cases has increased, and you can measure that, and you'll get a very high correlation value, close to 1. But I wouldn't say that, changing the number of pirates in the world is necessarily having any, impact on the number of cancer cases. So we have to be careful that just because we have an R value that is close to 1 doesn't mean that the two variables are, one is causing the other. Here's a little example. We'll get some data here. We have this shear box experiment where we have this box that has basically built out of 2 parts. We fill it with sand, and then we put a weight on the top. And then we try to push the top section of the box apart from the second one to shear it. So depending on the amount of weight on the top, we would expect that it would take more force to shear if we continued to use the same material within the box each time. So that's the experimental data here. We put different weights on top of the box, and then we measure how much force it takes to shear it. It would make sense that this would have a positive correlation, the more weight you put on the top, the harder it should be to shear it. Does it follow a linear pattern? Well, we can take our values here and plot them, which I've done just below here. And you'll see that, yeah, it is following a linear pattern. Do we have a bivariate normal distribution? Impossible to tell with so few values. So we're going to apply the formula, even though we probably don't have the right to. We would need more data, or we would need to know more about the situation before we made this assumption. But just so that this example would fit on my lecture slide, I kept it small. And so that we could calculate it basically, by hand. We'll just assume that we've met that condition. So to actually evaluate the correlation coefficient, I know it would be high based on, just by looking at it, I can see that that's a pretty nice linear relationship. The calculations involve products of x, y's, x squared, y squared. So I just built a table and calculated the totals here, again using Excel. So I could get these intermediate pieces of the equation, calculate the R value. It's 0.9656, which is pretty strong. You can see what 0.96, now looks like. We like our values, very high, 0.9 or better in, a controlled experiment. Maybe in a more social experiment, we'd have to, start trusting values that were lower, 0.7 or 0.8. But in a very controlled study, we'd like to have a correlation coefficient that's very high so that we can build a model for this that does a good job of making predictions, which is our ultimate goal here. We can do a hypothesis test. I know we've just spent like 20 minutes without doing one, so maybe it's time to do one. The hypothesis test that we can conduct is the correlation coefficient 0? Basically, is there no correlation or not? So our test statistic is a t-score. Our variable that we're testing our sample variable is R. So we're trying to see if R is far enough away from 0 for us to reject the null hypothesis that there's no correlation. So we can run through this test quickly. I don't believe Excel automatically gives us like the p-value for this test, so we'd have to do this one ourselves using this test statistic. Notice the degrees of freedom are n-2. That often happens. We have two data sets. We have our x column and our y column, so we lose 2 degrees of freedom. If we're going to do this formally, we'd need our good old step 1, which is the claim. What is the claim here? That there is correlation or that there isn't? Maybe we'll say that there is, because it didn't really say in our example. And by significant correlation, we'll say that rho is not equal to 0. Remember, R is the correlation coefficient for our data set, which is an estimate of the correlation coefficient for the entire population. So that's what we're conducting our test in here. This is our claim. Is that there is linear correlation. Look at it. I feel pretty good that there is linear correlation. We probably don't have to do the test in this example with a value so high. It's nowhere near 0. But just to show you how it's done. Step 2, you set up your null and alternative hypothesis. And our claim is the alternative here. So our null hypothesis we'll work under the assumption that rho is 0, that there is no linear correlation between these two variables. On to step 3, that's where we set our significance. 5% chance of rejecting the null hypothesis, even though it's true. Step 4 is calculate the test statistic, or step 4 is check our assumptions, which we didn't really check. All we can say is we have random data, assume bivariate normal. The formula for the correlation coefficient is considered fairly robust, so this assumption isn't too much of a stretch. Linear regression modeling can be abused, I suppose, in some situations where that is violated, but we find that this correlation coefficient isn't horribly thrown off even when you don't have this bivariate normal. There are ways to check for this in an indirect way, which we'll quickly run through later. The test statistic was, r minus rho over the square root of 1 minus r squared over n minus 2, and that's a t distribution. I added in the formula above, I didn't have the rho in it because the test is always null hypothesis, rho equals 0, but our r value is 0.9656, and then we're subtracting 0. And I believe we had 10 pairs, so it'll be 10 minus 2. And we get a test statistic of 10.5. That's a crazy big T. Step 6, this is a two-tailed test. Maybe we should do this one traditionally, because I know I'm not going to find 10.5 on my T table. So let's do the traditional method. In a two-tailed test, we'll take our alpha and split it in half, and we'll determine the cutoffs. So we'll have our T alpha over 2. I know we're going to be nowhere near these cutoffs. In our case, alpha was 0.05. So it's 0.025. And that's the area underneath the T distribution. The degrees of freedom are 10 minus 2, which are 8. And now we just have to look up these values in our T table, or we could calculate them in Excel, T dot inv dot, I think there's a 2T, dot 2T, and then you put in alpha and your degrees of freedom. Alternatively, we can just go and look at our T table. So we're in row 8. And we have 0.025 in our tail. So our test statistic there, our critical value will be 2.306. our value that we calculated was 10.5, which is clearly in the rejection region. So step 7, we'll reject the null hypothesis. And then step 8, get our conclusion. Well, our claim was the alternative, and we rejected the null. So that means we're supporting the claim. And because we rejected the null hypothesis, we get to say this rather strongly. We can say there is enough sample evidence to support the claim. So the sample evidence supports the claim that there is a significant linear correlation between the normal stress and shear stress. I'm just going to say between the variables. Our variables were x was the stress, the force coming down, or the perpendicular stress or normal stress, and then we had the shear stress. And we probably didn't have to do this test knowing that the value was so high, even though we had such a small data set. Now we get to go on to the fun part here. We get to actually build the model. We'd like to come up with the equation of the line that best fits the data. So we'll have a theoretical line that would go through the population, and then we'll have a sample line. So, using the notation here, we'll use Greek letters when we have a population, and then we'll use our English letters when we have a sample. We'll let b and beta equal the slope of the line, and we'll let an alpha be the intercept. Normally we write lines, y equals mx plus b. In stats, we write it slightly different. The a is the intercept and the b is the slope. It's a plus bx. And we use y hat mostly because of the whole issue of upper and lower case, or a Greek y versus a English y. I don't think there is a Greek y. Their alphabet's shorter. So often we use this y, usually call it y hat for the sample case. So we're breaking our rule of having a Greek letter for the population there. But I think you get the idea. We're at least keeping consistent with our Greek versus English rules for the parameters for the intercept and the slope. It takes a little getting used to calling the slope b. The reason that they statisticians have chosen to do it this way is you don't always have two variables. Sometimes you'd have a plus bx1 plus cx2 plus dx3. So it allows you to build that pattern. Right now we're just considering the two variable linear case, but obviously we can expand this to a multivariable case. So our goal is to be able to predict the y given an x. Because you often don't have a full range of data, so you'd like to be able to use this for interpolation for sure, and maybe sometimes we might use it even for extrapolation, making a prediction outside of our data set. Not necessarily recommended, but something we might have to do if in the absence of anything else. So the conditions for these intercept and slope values will be the same as what we had for calculating the correlation coefficient. So we're only going to apply formulas here that are involving a linear relationship, and we need a bivariate normal distribution in order to actually do these calculations. So we're going to come up with formulas for little a and little b, which approximate the actual values for alpha and beta. So here they are. Again, kind of nasty formulas. I didn't derive the ones for the correlation coefficient. I don't think I'm going to derive these either. They come from a method called least squares. Basically, to derive these things, we want to come up with a slope and an intercept for our data such that we're minimizing our error. Maybe I'll just do a quick little sketch. Suppose I have a data set that looks like this. You might think that the best line is here. And maybe I think the best line is here. And maybe somebody else thinks the best line is there. Right? We're trying to come up with the slope and intercepts for these lines, or for the best line. And to do that, we try to basically minimize the error between the line and the points that we have. So say I have the line here. I would want all of these distances to be as small as they can be. And to adjust that, I just keep moving, jiggling that line around until I found the smallest total area, or error, I should say. So those differences, I would have the actual y values minus my predicted y values. These y hats are the y values on the line, and the yi's are the y coordinates of the actual points. I want to minimize those distances. Some are positive and some are negative. So, we do that old trick of squaring everything. We'll try to find the smallest squared distance. And we want to do it for all the points, so we would be summing these up. If I called this equation, say Q, we could replace our y hat with our model. It's a plus bxi. And now to come up with these equations, the math isn't too bad. You've already had multivariable calculus. You take the derivative of our equation with respect to little a, and then you take the partial derivative of this equation with respect to little b, and then you set those two equations equal to 0, and you solve for a and b. That is the method of least squares. So the derivatives aren't too bad because you're considering basically everything to be a constant except, a or b. So it's actually not too bad. The algebra obviously gets to be a little nasty once you have the two equations. You have to solve them. It's two equations with two unknowns, and then when you solve them, you get a and b. And this process extends to however many variables you had. If this were, 3 variables, it'd be a plus bx1 plus cx. And then I'd take partials with respect to A, B, and C, and I'd have three equations with three unknowns, and I'd come up with my three estimates here. There's a bit of a shortcut for the intercept after you know what the slope is. So if you grind out the slope equation, you can pretty easily get the intercept because y bar and x bar are pretty easy to calculate. You can do some algebra to prove that as well, but we won't. Again, we're going to rely on the software to give us these results. Back to our shear box experiment. We had our data. It looked linear. We calculated R already. In Excel doesn't like to give the correlation coefficient. It gives R squared. It doesn't like to give you a negative number. Like this value plotted on the chart here is our little r squared. We call that our value, the value of r, the correlation coefficient. When you square it, it gets a new name. It becomes the coefficient of determination. So that's what Excel likes to give. Excel also is happy to give you the equation of the line. So it calculates the slope and the intercept using the equations that we just sort of derived up above. I did the manual calculations just to confirm that because I had already calculated these totals for the sums, the products and the squares, etc. So you'll see that these values by hand match the default output from Excel. To get this on the plot here, I just right-clicked on my data set and said add trend line, and then I made sure to display the equation on the chart. So we'd never really do these things by hand. We will use Excel to come up with these. But we get our model. The model is given on the plot there. I've also written it here. So we have our intercept and our slope. Even your calculator has the ability to calculate the slope and the intercept. You just put your calculator into another mode. We've used a stat mode on our calculator. Let's see I wonder if I have that even. If I click on our calculator and go into mode, and we've been in stat mode, and we've used this SD, meaning single data mode, we can now go into mode 1, which is line mode, and then you can enter your values. For this example, say our first data point was 11:15, so I type 11, and then I believe you have to hit a comma, 15, and then your data button. And now that point is in the calculator. And then you have to repeat it, 13, 17, and hit your data button. And you keep doing this, 17, 19, data. So say I have the three values in there. If you look above your buttons here, your correlation coefficient is R, so it's alpha and the divide sign, and it gives me the correlation coefficient. I only did the first three values, and it was still a nice high correlation value. And you can get your slope and intercept from the buttons, your parenthesis buttons. So alpha, left bracket is your A, and alpha, right bracket is your B. So it gives you the equation of the line. You probably never noticed it. Your cheap calculator could do so much. But you probably never use your calculator for such a thing. I would much rather use some software where I can plot the thing first because you shouldn't even do those calculations if you don't have something that looks at least somewhat linear. So really the calculator it's cool that it can do it, but without the scatter plot, it's kind of useless, I would say. Once we have the equation, we can finally make a prediction. We had our equation was y hat equaled 3.39 plus 1.05 times x. And now suppose you wanted to know how hard is it going to be to shear this thing if I put a normal stress of 16. So that's x. Plug that value into our model and you get 20.24. Let's see if it makes sense from the picture. So we estimated 16. So 16 is a value. We didn't have any values around 16. And we ended up with a number close to 20. So we used our model to kind of estimate a value where we didn't really have any data, but the trend of our data makes us feel somewhat confident in that prediction. We'd have to be careful if I said, predict when x equals 50. We have no idea if this continues along that same trajectory. Who knows what happens after this point. So the answer to that is don't predict a value of 50. It's way too far off the end. But if you said, what's going to happen if you put, 28 or 30 on top of this box? Well, maybe you could feel like your result might be somewhat reasonable there. So ideally you don't go off the outside of the range of the value that you actually have, but if you don't have anything else, it's better than nothing. In fact, if you had absolutely nothing else, it might be the best you can do to predict, a value out here at 50. But I wouldn't feel very good about my prediction. So that's a little note here. Be careful about your predictions. Try to predict within the range. This value here is probably not the exact answer. If you put 16 on top, is it going to be 20.24? No, it's going to vary. So if this is an estimated value, well, I guess there's a theoretical correct value. Therefore, we could do maybe a confidence interval for the actual value using our predicted value. But before we can do that, we need to define something else. We need something called the standard error of estimate. And we did kind of allude to this already. The standard error, I sketched it out. I couldn't wait to show this to you. The standard error is basically, we're trying to gauge how far are the points away from the line. In this one, you can see the points are quite close to the line. We're trying to find the average distance of these points away from the line. And that's what standard error is. You look at the numerator of this, and it's basically the sum of the squared error, and then we divide it by however many points there are, biasing it a little bit, n minus 2 instead of dividing just by n, and of course taking a square root to fix the squaring issue. So, and to keep our units then the same, so that these distances are still in the same units as whatever we measured our y variable to be. In this case, kilonewtons per square meter. So this formula isn't too bad to calculate. Either even if you're doing it by hand, it does have a calculation formula that makes it a little easier if you've already calculated your slope and your intercept, which you likely would have. But again, we'll use Excel to do this. I don't believe your calculator actually has a built-in standard error button, but it does have the buttons for, if you look around on it, we have the sum of the xy. Like this part of the equation is on your calculator under button 1. So you say alpha 1. I don't think I got it. Alpha 1. Oh, I lost my mode. Must have turned off my calculator. So mode 1, linear. And if we put some data in, say 1, 2, data 2, 9, data, and 5, 22, data. So I have 3 values in there. If I want to know the sum of the products xy, it's under button 1, so alpha 1. And if I need to know the sum of the y values, that's under button 2, alpha 2. So you have everything you need to do in order to calculate this. The A is under alpha bracket here. So it wouldn't be too hard to calculate that. But we have Excel, so we don't really need that. I did it by hand just to show you. I used all our intermediate values here. The standard error for our example was 1.1. So basically, some values are further away from the line, some are closer to the line, but on average, the distance away from the line is 1.1 units in the vertical direction. Which, the smaller that is, the better. I mean, your line is fitting better the smaller your standard error is. So this number, it will be smaller the closer your correlation coefficient is to 1. They're linked that way. Here's our prediction interval then. It involves a standard error. When you calculate your y hat for a particular value, so you have some value x0. In our case, we did a prediction for 16. Remember what we plugged in 16 into our model, and we got a y value that corresponded with that. I believe it was 20.1 or something. Without scrolling back too far, I think I have it written down somewhere. Don't get dizzy here. It was 20.24. So we made a prediction when x was 16, y was 20.24. And our equation was y hat was 3.39 plus 1.05 x. So this predicted value we know has error. It isn't exactly what it would be for the whole population. So the population value is within some range. So we calculate error based off of this formula. It uses a t-distribution with n minus 2 degrees of freedom, similar to what we had for when we did our hypothesis test for the correlation coefficient. So this is tedious to calculate, and sadly, this function is not built into your calculator or Excel, so we will actually have to calculate these intermediate pieces if we want to do a prediction interval. Other statistical software obviously does a better interval. This would be built in. I'm not sure why it's not in Excel, actually. We call it a prediction interval, but it's just a special confidence interval. So suppose we wanted to do this interval for the data that we had. We just have to grind our uh, through our math and plug in the intermediate values here. The maybe the trickiest part is getting standard error, which is above. So I guess so. Really, the only hard part we have is our t-score, which we already did when we were doing our hypothesis test for the correlation coefficient. We found these critical values in T alpha over 2, because luckily we're still doing 95%. And the degrees of freedom are the same for this as they were for the other one. The degrees of freedom will be 8. When you look that up in the t-table, we saw it was 2.306. And now we can calculate error. Error is this t-score, 2.306, times our standard error. Luckily, we've been working through this the whole time. The standard error we just calculated, it was 1.1. Might as well put as many decimal places as I had there. And then we have 1 plus 1 over n. In this case, we had 10 pairs of values. That wasn't too bad. Our x naught was the value we were estimating for x, so that was our 16. And then we have x bar, which I guess we could get from our data here. We have the sum of the values here, so it's 172 divided by 10, so 17.2. So this isn't too bad. We had the sum of the x squareds. I'm going to slide back up there and grab that value. That was 380 or 3080. And then the sum of the x's, which was the 172, but we're squaring it. Punch that through your calculator, you get 2.65976. So we would say that the actual predicted value is 20.2 plus or minus 2.7. And what are the units there? They were kilonewton per meters squared. Or you could write it in that interval notation. 17.6 is up to 22.9. And we're doing this at 95% confidence. So when, this is for when x equals 16 kilonewton per meter squared. When x is 16, we think y is somewhere in this range. That's basically what we came up with. It's a little tedious to do. Sadly, the software doesn't just spit out that solution for us. So we would have to do this. But we can get the intermediate values using some software. So not too bad. We can, we are estimating the slope and the intercept of the equation. So certainly we can come up with confidence intervals and hypothesis testing for the slope and the intercept. Here are the formulas for the slope parameter. I find that one to be more interesting than the intercept. I don't really care if the intercept is 0 or what the intercept of my line is, but if the slope is 0, that's really bad. Uh, if you have a data set and it's random, the slope would ultimately be 0 for the line. So a slope of 0 is a bad indicator. It's hard to make a prediction. So that's the hypothesis test that we evaluate. Basically, is the slope of my line 0 or not? So, and here's the test statistic. It's a t-test. So confidence interval also uses t. Degrees of freedom are n minus 2. We could do an example using that, but I think I'm going to cheat and just use Excel to do that, just to show you quickly how that's done. So here's Excel. Here's our data. I'll quickly show you how you make all this stuff. You can just grab all the data and insert a scatter plot. And if you want the equation of the line, you can right click on it, add trend line, and then you get a choice of what type of regression you want to do: exponential model, linear, logarithmic, polynomial, etc. We want linear, and we want to make sure that we display the equation on the chart. And I also want to see the R squared value. And then, if you don't like where it put it, you can move it wherever. So that's quickly how you make one of these things. Certainly, you'd probably want to add axis titles. So add axis titles, and then label this thing all nicely. Give it a nice title. So that's how quick and easy it is just to get the rough chart. We have the slope and the intercept given there. We have our R squared given there. Excel also has another more extensive package for doing linear regression than just adding a trend line. Back when we were first doing this stuff, we added a statistical package in. I'll remind you how to do that. You go to File and Options and Add-ins, and then you make sure you add this analysis tool pack, clicking the Go button to get it to add. I won't press it, just I don't goof mine up in some way because it's already in. Yours is probably already in on your computer too. When you do that analysis tool pack, it adds to your data tab another menu option called data analysis. And under that, we've used this a few times now. We did analysis of variance, we did the F-test, we did descriptive statistics, we made histograms, we did a t-test, and now you'll see that there's also regression. So you can click on that. Be careful when you use this regression tool. It asks for 2 inputs, and it asks for the Y value first. So make sure you go and highlight your Y's. And then the next one is going to highlight your X's. And then I did include the labels when I highlighted my data. If I wanted to create 99% confidence intervals, this would be my chance to make it 99% there. And then I'll ask for all these weird plots, and maybe I'll quickly just talk about them. You have a lab on this where you'll do this yourself. So I just give you a quick idea. I don't know why by default it doesn't just give you everything. And then I'm going to choose to put my results, say, right here. Maybe I'll put it in that cell is kind of weird. So I'll put it just below it. And now the results will end up on this page rather than on some other tab somewhere. And you just click OK. And it gives you a bunch of output here. It gives you the R square value. And you can see that it matches what we had from the fit and from when we did it by hand in the lecture. We have a few other things. We have adjusted R square, which is useful when you have more than two variables. The problem with the R square is that as you add more and more variables to a model, the R square drops. Even if you're adding variables that have, almost nothing to do with it. So, like if in this case, I could add the weight of the person who's conducting the experiment. And if I did that, added that data to the model, my R square would drop because I've added more information. However, it wouldn't be good information. So that's why there's this thing called adjusted R square. You can see that our standard error, remember we calculated SE, that's right here. So we have R squared there. Adjusted R squared is for multiple data sets. We have our N. So Excel gives that nice summary. Excel also gives an ANOVA analysis. This is a test to see if all of your coefficients are zero. So this is a hypothesis test of alpha, the slope equals the intercept equals zero, which would mean you have a bad model. That's the null hypothesis here. So we would like to reject this null hypothesis in order to, have any faith in our model. And in this case, you get a p-value of 5.86 times 10 to the minus 6. So we would reject that. So the analysis of variance is another. We used it to compare multiple means, but it can also be used to compare other things. In this case, our slope parameter and our intercept parameter. And we would reject that they are zero, which is good. I don't really love this section of this, mainly because I don't care if the slope is zero. I only really care about the intercept being zero. And that's what you'll see down below in the next part of the output. The first row is information about the intercept. So our A. So in our case, our A is A equals 3.39. And our B is our slope. That's the second row of this thing, 1.05. And it gives us basically, I'll make these a little bigger. It gives us, maybe not that much bigger, confidence intervals. So we have a 95% confidence interval here that says our slope is somewhere between negative 0.65 and positive 7.4. Our actual observed value is 3.39, but the theoretical value is somewhere in that range. And we have the same, did I say slope? I meant intercept. We're in the first row. The second row is the confidence interval for the slope. Our slope is somewhere between 0.8 and 1.28. If we use 95%, remember I added 99% when I asked for this, so it gave me 99% confidence intervals as well. It also gave me the p-value for the hypothesis test. So the hypothesis test is the intercept is zero, or the hypothesis test is the slope is zero. And then we have these p-values where we could either reject that or not. So an example, null hypothesis, intercept is zero. Alpha equals zero. We would fail to reject that because our p-value is 0.08, which is bigger than 0.05. And then we have another hypothesis test there where slope is zero. But we will reject that because the p-value is, tiny in scientific notation there. no matter what you picked for alpha there, you would reject that the slope is 0, which makes sense. You don't lose sight of the, take a look at it. That doesn't look like it has a slope of 0. In fact, it was, just over 1. So that makes sense. But it's significant enough. So if we were going to do our hypothesis test, as it was stated over here, continue our example, test the hypothesis test that the slope is not 0. So that's our null hypothesis, is that we have a slope not equal to 0. We could quickly write that up nicely using the data that we had from the other page. Null hypothesis, alternative hypothesis. The slope parameter is beta. The null hypothesis is that it is 0. That's step 2. Step 1 is what the claim is. Then move on to step 3, pick a significance level. I hate to write alpha because these parameters are also alpha and beta, so I'm just going to say significance. 4, assume we've met the assumptions. That's the bivariate normal distribution issue. And then 5, we calculate our test statistic, which is a t-score. And I could grab it off of my Excel output. My test statistic is given right here. The test statistic for the slope was 10.5. Oh, that's weird. It's the same as it was for our correlation coefficient. So t was 10.5. Our p-value, what was it? 5.86 times 10 to the minus 6. What was it? 5.86 times 10 to the minus 6? So we'll reject the null hypothesis, which means we'll support the claim that the slope isn't 0. This is really rough. But you get the idea from that. You can use Excel to get those values. They're just in that standard output. When you're talking about, I said I just waved my hands at bivariate normal distribution. We could look at some of the other plots that Excel gives us. It does a normal probability plot. We learned in another lab that a straight line means you have, you're achieving normality. So this is a nice indication that things are going okay. What else do we get? This is just a crude version of what our nice plot. It's the blue values are the actual values and the red values are the predicted values at each of those same points. So it's basically our scatter plot with the line sort of on it. Another plot that it gives us, get this out of my way, is the residual plot. Residual is a fancy word for error. So these values on this plot are basically the distances that the points are away from the line. When we calculated standard error, we summed up the squares of these values. So these are just your basic errors. And what we want to see on this plot is randomness. We want this plot to be completely random. If we see a pattern in these residuals, that means that we're either systematically over or underestimating at some points on the line. where we should be equally over and underestimating. So this should be, you know, the center line here is 0. We should have just as many points above and below 0, and it should be randomly achieved. If it's not, then maybe we shouldn't be doing linear regression. Like maybe the data is curved, so that shows up in this plot. So looking at these plots helps us feel better about achieving the conditions or assumptions required to do all this stuff. So if we look at these two pictures and we see a straight line in this one and a random scatter in this one, now I don't feel as bad about uh, that step 4 of our hypothesis test where we say, oh, I think the assumptions are okay. Well, there's at least a visual way to check that. I think that's what's given down below are the, the calculations of the residuals so that those plots could be made. So that's the Excel output. You have a whole lab, you do a tutorial where you work through this stuff, but I may have just saved you. You can go through that pretty quickly now since I just did it. But it's kind of nice to see what power Excel has for solving these things. I think I'll only ever ask you to do, really the slope is the more interesting parameter than the intercept. See you in the next lecture. Have a good one.